Day 4 of Unit 1. Unit 1's all about review of things that you needed from pre-calculus that we'll use later this year. Lesson 4 here is on arithmetic and geometric series. Probably starting in about January. We'll do lots of series, deciding if they converge or diverge. Before we do that, let's review what you should know about sequences and series. So the first type of sequence, first of all, a sequence is just a list of numbers. The first type is an arithmetic sequence. Arithmetic means we're adding the same thing over and over again. So it's like 5, 11, 17, 23, 29, 35, 41, and so on. Plus 6, plus 6, plus 6, plus 6, plus 6. So if we're adding the same thing over and over again, it's called an arithmetic sequence. And we can get a specific term from an arithmetic sequence by using the formula a sub n equals a sub 1 plus the quantity n minus 1 times d. A sub n is the nth term, whichever one we're looking for. A sub 1 is the first term. N is the number of terms. And D is the common difference, whatever we are adding over and over again in the sequence. The difference between consecutive terms. We also have a formula for an arithmetic series. A series means we're taking a sequence and we are adding the values up. So now we want the sum of an arithmetic sequence, which is the sum of the first n terms is equal to n over 2 times the sum of the first and the last term. N over 2 times quantity a sub 1 plus a sub n. We also have geometric sequences and series. A geometric sequence means instead of adding or subtracting the same thing over and over again, we are multiplying or dividing. So geometric would be like 2, 6, 18, 18 times 3, 54, 54 times 3, 162, I think, and so on, times 3, times 3, times 3, times 3. The formula for a geometric sequence is the first term times r to the n minus 1. Everything stands for the same thing. Only new variable we have is r, which is the common ratio. And then if we're going to add up all those terms, the formula is given by this guy here. A sub 1 times 1 minus r to the n over 1 minus r. And let's look at an example here. Example 1, we're going to do this twice, once without a calculator, and then we're going to verify our answer with the calculator. Make sure you know how to do it both ways. This asks us to evaluate the sum as I goes from 4 to 100 of 2i minus 7. First thing we need to do is determine if we have an arithmetic series, a geometric series, or neither one, something else. So we can do that by plugging in values. We're going to start by plugging in 4, gives us 8 minus 7. Now you would plug in 5, 10 minus 7. Plug in 6, 12 minus 7. 14 minus 7. 18 minus 7. I skipped one. Plugging in 8 gives me 16 minus 7. And hopefully you can recognize that this series is arithmetic. Plus 2, plus 2, plus 2, plus 2. So because it's arithmetic, we're going to use the formula for an arithmetic series, which says the sum is equal to the number of terms, talk about in a minute, divided by 2, times the sum of the first term, 1, plus the last term. We currently don't know. So we plugged in 4, 5, 6, 7, 8. Should plug in 9, 10, 11, 12. All the way up to 100 is the last number you would plug in. So plugging in 100 gives us this last term right here, which is 193. To figure out the number of terms we have, you could either do it logically. Think, well, I plugged in 4, 5, 6, 7. I plugged all the way up into 100. So 100 minus 4 is 96. But I plugged in both the 100 and the 4, so we have 97 terms. If that didn't make sense to you, another way you could do it is think about the sequence formula. A sub n, we just said, was 193, and the first term is 1. And I don't know how many terms there are. I know the common difference is 2. And we can solve for n. Subtract 1. I distributed this 2 here. Add 2. And divide both sides by 2. And we get that same value, 97. To evaluate this without a calculator, a little arithmetic here. 193 plus 1, that's easy. 194 divided by 2, we actually just did, is 97. And let's just leave it as 97 squared. You can multiply out 97 times 97 if you really need to. But to do it with a calculator from the start, we don't need to multiply all this out and list out all these values. We can type this into the calculator. Just want to make sure you know how. Couple different ways you can type it into the calculator. The easiest way is to push the alpha button and then the window button. Alpha window pulls up the screen. And notice right there, sum is number 2. Another way you can do it, I think it's under math. Yeah, math, and then scroll all the way down to the bottom. 0 is summation. Either way, it'll pull this up. We want I to be 4. Instead of I, let's use X. X starts at 4, goes to 100. If we're using X instead of I, 2X minus 7. And the answer is 9,409. Which hopefully is the same thing as 97 squared. Yep. Example 2 asks us to find the sum of the first 50 positive even integers. Find the sum of the first 50 positive even integers. So let's start listing them out. We're going to add up 2 plus 4 plus 6 plus 8 plus the 50th positive even integer should be 100. This is an arithmetic series. Sum of an arithmetic series is n divided by 2 times the sum of the first term and the last term. (102) divided by 2, so we get 50 times 51. $25.50. We're going to skip that one. Don't worry about that. Example 4 asks us to use summation notation to represent the finite series. So a finite series means that the series stops. It doesn't go on forever. Notice plus 50 and it stopped right there. Eventually, we'll talk about an infinite series. So this finite series looks like we are adding 4 each time, plus 4, plus 4, plus 4, and so on. So it's an arithmetic sequence. To get the nth term of an arithmetic sequence, notice I'm starting at 2, and I'm adding 4 over and over again. If I put an n right there, notice when I go to make the sum, if I start my I equals 1, if I plug in 1, notice my first term is 6, and this says my first term should be 2. So you can either use the formula for an arithmetic sequence, that would work great, and then simplify it. So 2, first term, plus n minus 1 times the common difference, distribute, and combine like terms. This should be 4n minus 2, or 4i if we're using i's. N's are fine, just be consistent. It's a bad I. Another way you could get this is, I'm plus 4 every time, so I know it's 4i. And if I'm going to start with I equals 1, 4i, and I need to get to 2, so it's going to be minus 2 to get to 2. The other thing we need is how many terms we have here. To figure out the number of terms, kind of like example 1, I would go back and use the sequence formula. So I want 4i minus 2 to be 50. I want to know what I value gives me that. And that goes right here. Part B. 2 plus 6 plus 18 plus ... plus 13122. This appears to be a geometric sequence, times 3, times 3, and so on. So we want to have the sum. I starts at 1. I don't know what term that is. Formula for a geometric sequence is the first term times the common ratio to the n minus 1 power. To figure out this term, you'd be allowed to use calculator here. You could guess and check and just times 3 and count up how many times you pushed enter to get to 13122. The other way is to again use the sequence formula to say, okay, I have 2 times 3 to the I minus 1. And I want to know what I is to get that value right there. Divide by 2. Gets me 6561. We'll talk about that one in a minute. And then to solve this, i's in the exponent, so you need to take the natural log of both sides. And then I'm going to move the I minus 1 out front. Divide both sides by ln3. So I is 9. And part C, it does say plus ... So this one is an infinite series. So we know we have some. We're going to start I at 1, go up to infinity. This one we've got two different things going on. In the numerator, I'm adding 2, plus 2, plus 2, plus 2. So the numerator is an arithmetic sequence. So we're going to do that the same way that we did part A. So I know I have 1, and I'm adding 2. So I have 2n minus 2 plus 1, 2n minus 1. And you can double check that. Plug in 1, gives me 1. Plug in 2, gives me 3. Plug in 3, gives me 6 minus 1, so on. Oh, on the bottom, I've got times 4, times 4, times 4. So on the bottom, we need to do it the same way we did this part here. It's geometric. So I have the first term, 2, times 4 to the n minus 1 power. Notice I used n here, so I should probably use n down here also. Doesn't matter if you use I or n or k or w, as long as you're consistent. I and n are the most common. Again, you can check that. Plug in 1, gives me 4 to the 0. 1 times 2. 2. Plug in 2. 2 times 4. Yep. Plug in 3. 2 times 4 squared. 4 squared 16 times 2 is 32. This one, we want to take a look at if a series converges to 0 or not. We have series here. We want to know, do these series converge to 0? Or does the sequence, it's not the right word here. Sequence is the list of numbers. So if I list these values out, if I plug in 1, the first term's 10. If I plug in 2, 5 times 2 squared. If I plug in 3, 2 to the third, 8 times 5. Plug in 4, 16 times 5. Times 2, times 2, times 2. And notice we are not getting closer to 0. It is not converging to 0. This is a big fat no. What if we have 40 times 1/2 to the n? 40 times 1/2 to the n. So if I plug in 1, I get 40 times 1/2. If I plug in 2, I get 1/4 times 40. Plug in 3, I get 1/8 times 40. Notice I'm multiplying by 1/2 over and over again. So 2.5, 1.25. Now what is next? 0.675, I think. And notice this time we are getting closer and closer to 0. Question is, how can we tell if the sequence is going to converge to 0 or not without listing out the values? First of all, it only happens on a geometric sequence. Arithmetic sequences will not converge to 0. So if I'm like subtracting 2, so if I have like a big long sequence and I get down to 8, 6, 4, 2, and it looks like it's getting closer and closer to 0, and it does, but then it keeps going, so it does not converge to 0. So the only ones that will, at least the only ones we've talked about that will, are geometric ones, but not all geometric ones. Geometric ones where our R value has to be less than 1. It has to be less than 1. But not everything less than 1. Because if this were like times -2, and I plug in 1, now I get -10. 2 gives me positive 20. 3 gives me negative 40, positive 80, negative 160. But this one here, if this one were negative, it would work now. It's still getting closer and closer to 0. So R has to be less than 1, but it has to be bigger than negative 1. It has to be in between negative 1 and positive 1. You'll also see that written a lot. The absolute value of R is less than 1. Those mean the same thing. All right. Finally, so if the sequence converges to 0, that's what this tells us, then the infinite geometric series, you don't need to necessarily list this out. You can cross that out. So if we have a sequence that converges to 0, a geometric sequence that converges to 0, we can get the infinite sum using this formula right here. That formula only works if the absolute value of R is less than 1. A sub 1 is the first term. R is the common ratio. So example 5 asks us to find the sum of the infinite geometric series. Notice we do have a geometric series here, mainly because it tells us we do, but you can verify that by 9 times what gives me 6. If you're not sure, just write 9x equals 6. 9 times 2/3. 6 times 2/3 gives me 4. 4 times 2/3 gives me 8/3, and so on. So my common ratio is 2/3. Notice the absolute value of that common ratio is less than 1. So we can use this to evaluate the sum of the infinite geometric series. Formula says the first term divided by 1 minus R. 1 minus R is the common ratio, 2/3. And I get this series has a sum of 27. Notice we could use the partial sums to verify. So we've got 9 plus 6 plus 4 plus 8/3. So those terms that are given add up to that. The next term would be 8/3 times 2/3. We're getting closer. So that next term was 16/9. So the term after that would be 16/9 times 2/3. And so on. Notice it's starting to get closer to 27. Probably the best way to do it would be to use a sum on your formula here and say x is 1. Go up to like 15 maybe should be enough. Of 9 times 2/3 to the n minus 1. So notice if I do it 15 times, I get 26.938. If I do it even more times, it's going to be even closer to 27. .9989. It's awful close to 27, even after just 25 terms. And you could keep going. What if we do like 50? I'll bet it's really close. So close, it might even spit out 27 itself. Oh, that's awful close to 27. Anyway, that's all I've got. Homework should be listed on Google Class.